All right, so welcome to the Zoom on September 6th, 2024, in preparation for the first test. And the question that came up was, if you want, do you have to use the quotient property, for example, on a derivative? Not necessarily. In fact, in many cases, in fact, I suggest try not to. Only use it when you absolutely have no other choice. I'm going to go to my overhead camera here. Give me a moment. And now the quality is not the best. Hopefully you can see that okay. But if you got a function like f of x equals, let's say, x squared take away 9 on top and x take away 3 on the bottom, and you were asked to find its derivative, in a case like this, I would not use the quotient property because in this case you can actually simplify the function by factoring and canceling. In fact, you get x plus 3, x minus 3 on top, x minus 3 on the bottom. Those cancel, so your function is just x plus 3. Therefore, the derivative is just 1. It's actually a straight line of slope 1. The only caveat is that x can't equal positive 3 because that's where you have a 0 in the denominator. That's it. That's really the only, for a function like that, that's good enough. If you were to use the quotient rule, you're going to have to mess around with simplifying it. And I don't know if you want to do that. So yeah, you've got these properties available to you, and you use whatever works. So what I'll do is I've got Affinity up, and I can go there if anybody has any questions they want looked at. So the usual routine on these kind of Zooms is it's basically question driven. So I'm willing to take any questions that you may have, and I am recording so that this will be available later on if you want to review it. So does anybody want to jump in and ask a question?
A quick question.
Uh-huh.
I'm having trouble with the squeeze theorem. I
Okay.
kind of get the concept that if there's a constant, we're gonna have our two policemen and a drunken guy, but
Okay.
it's hard to remember. It's from 2.1, 5, and 6 homework.
Yeah, let me bring it up. I'll bring it up on the give me a moment. 2.15 and 6, you said?
Correct,
Yeah,
yeah.
okay. I'm gonna put it on the share screen. I think that's it. All right, so these are two examples here. One of them, they're both similar but slightly different. Let me copy them down. I actually covered this one last week too. This one's a popular question. Um, you have x times sine negative 10x, and the other one is negative 10x to the 8 sine 1 over x. All right, I'm going to temporarily then go away from this screen. The sine function, especially if it's just sine of 1 over x, and actually the negative 10 here doesn't really do anything. It just makes it's still the same shape, but the sine of the 1 over x function's actually got a pretty bizarre shape. It's like a sine wave that tightens up as you get close to the origin on both sides, and it spreads out as you get farther away. And it's not defined at 0 because you get a 0 in the denominator. So at the origin, interesting enough, it's just nothing there. But if you multiply it by uh, what's they call an envelope function, you can actually press it between it. So in the first case, the sine wave is actually caught between an x and also a negative x. So the function x, y equals x is just 45-degree line, y equals negative x is that, and this sine function is actually caught in between, and it's doing something like this. Okay. Whereas same thing down here, but its envelope functions are again, this negative 10 can be ignored. It's the x to the 8 that's kind of the big deal. You've got these come down and hit the origin like that, but here it's just the way they, the difference in the way they hit the origin. If you ignore the sign for now and you ignore the negative 10, and you just look at the x to the 8, its derivative at the origin would be 0. And so these two envelope functions both have derivative of 0 at 0. So will the, so basically I would write it this way. In fact, I'm going to ignore the negative 10 for now. It would look something like this. So the x to the 8th sign of 1 over x is pressed in between these two bounding functions. Both of these have slope 0 at x equals 0. So therefore, this has to have slope equals 0. Okay. The difference here is that this one does not. This function actually has, it, if I were to write it as negative x is less than or equal to x sine negative 10 over x less than or equal to positive x, at 0, this has a slope of -1. This has a slope of +1. And the question then is, what's going on with, sorry for the crampedness, it's not being pressed in. You can't infer that its derivative seems to be bouncing between -1 and 1. Does that make sense?
Thank you.
Yeah, again, this is 2.15 and 6. This is one of those questions, it would be hard to do directly because it's still not continuous at 0. This is one of those functions that they artificially make continuous by actually defining the function to be 0 at 0. Okay. All right, any questions? Somebody said MAT265 part 1 study guide number 14. And I'm not sure what that is. Where'd you see the study guide at? I mean, there's stuff floating around out there.
I think the one that this study guide was pulled from is one of the overall Math 265 study guides that I think is on one of the ASU pages.
Okay, yeah, those probably, I mean, some of those are like 15 years old. I mean, the math is still valid. Also, sometimes the ASU tutor centers will produce their study guides too, and those circulate as well. And I don't know what's on them. Somebody says here we have a question 24 on 2.3, finding the point where the normal line intersects the parabola a second time. All right, let's take a look at that one. That's 2.3 number 24. Let me bring it up. We will find it first. So lots of questions on this one. All right, I'm going to share the screen. So here it is. 2.3 number 24. At what point does the line normal to the graph of y equals 5 minus 5x plus x squared at 1, 1 intersect the parabola a second time? Okay, let's go ahead and work this one out. Okay, so what we need to do, we need to figure out the slope at 1, 1. So the derivative is -5 plus 2x. So we plug in a 1, -5 plus 2 times 1, and you get -3. That's the slope of the tangent line of the function here at 1, 1. Its slope is 3. The normal is a perpendicular line, and the normal has a slope of, it's going to be the negative reciprocal, so it's just going to be 1/3. All right. Well, we already know that the point is 1, 1, so we use the formula, this old formula from algebra, the point slope equation for a line, to figure out what its equation, the equation of the normal line is. So we just pop in the numbers. We just work it out. Let's see, we third x take away a third. Oops. And you add 1 to both sides, you get 1/3 x. So if you add 1, you get plus 2/3. All right, that's the equation of the normal line. And what we're then going to do is set it equal to the original function to find where they intersect. So you just set this guy 1/3 x plus 2/3 is equal to the original function up here. And you just work it out. It becomes an algebra question. If I collect terms, I'll do it on the right side. It's a little messy. 5 take away 2/3, that's 13/3. -5 take away a third, that's going to be -16/3 x. This guy doesn't change. And I'm going to get rid of the 3's, so it's going to look something like this. Okay, let me pause here. I'm sorry, the question is, why is the slope reciprocal again? Perpendicular lines. If you know the slope of one line, then the slope of its perpendicular is going to be negative reciprocal. That goes back to, I guess, geometry. All right, let me pause here for a second. Is that, so far what I've done makes sense? If not, let me know. I'll assume silence means yes. Okay. All right. So anyway, yeah, you're basically setting the equation of the normal line equal to the original function, which is what I've done right here. I collected my terms. At this point, you just need to work out the quadratic here. If you want to use the quadratic formula, that's fine. It'll work. You just need to be careful with it. This one does factor. I know that I can pull out a 1 because I knew that from the original problem is that 1. So I just got to figure out, it looks like it's going to be 3x and a 13. It looks like it's going to be that. So I get two answers. One of them is 1, which is not a surprise because that was where the original point was. The other one looks like it's going to be 13/3. So it looks like that's the x value of the other point. So you just pop it in, and I don't have my calculator handy. Oh yeah, I do. Let me do it real quick. So you put the 13/3 into the original function up here, just to pop out a number. I'll do that real quick. Um, and I get 19/9. If you're going to use decimal values, take it out about 4 decimal places to be on the safe side. And the question was now finding the roots, and that is correct. All right, that was a fun question. All right. Again, I'll throw it up. So let's see. So it's basically just finding numbers and plugging in the original. Yes. So it wants the coordinate of the point at which they intersect. So we had to find the 13 thirds here, and then the very last step is just pop it into the original function way up at the top, and then just work out what its y value is. So Maggie says 2.2 number 5, the discontinuity question. All right, let me back out of this. Let me go to my hold on. Let me go to my Edfinity first. Number 5. All right, let me share the screen. So here's what my question looks like. Yours will probably look similar. Let's see what we got going on here. Function is x squared plus 8 when x is less than 0, and 8 when x is greater than or equal to 0. Sketch the graph of f and put a number 1 in the box when you're done. All right. Find the value of x where f is discontinuous. If there's no such value, put in none. Find the value of x where f is not differentiable. All right, this is a good question. The graph, let me draw it real quick. It's going to be, you know what? Let me do this. I'm actually going to go to Desmos. I can do it by hand, but I'm going to show you Desmos if you don't mind. Let me go to Desmos because this will be on your. Okay, let me share that. So here's how you type in a discontinuous function. You type it in as a function, let's say x squared plus 8. But then you use the curly brackets and you type in this case, x less than 0. All right. Then we do it again. We have y equals just 8. And this will be for x greater than or equal to 0. And there you go. That's a nice looking graph. What do you guys think? So it's got a nice shape like that. All right. Everybody see what I did there using the curly brackets for, this is really nifty. Calculators don't do this at all, or they do a terrible job of it. All right, so back at the screen here. Yeah, so the question was, well, I'll go over each case. This one actually is continuous. So it's clearly continuous at 0. That's actually, oops, it's actually continuous everywhere. The question is it differentiable? Because when you have these kind of functions that are built in bits and pieces, you want to avoid corners. Now this one is actually differentiable. If I come down here and I do a derivative, I get 2x when x is less than 0, and I get 0 when x is greater than 0. And technically at 0, I have to be a little careful because that's not yet determined. So what I can do is I can take on the left side, notice that as x approaches 0, the derivative also approaches 0. So actually, in this case, it's 0 on both sides. So yes, it's differentiable at 0. And it is 0, so it actually is the derivative well. Yeah, so the question was, if Desmos can also show us where the holes, yeah, it doesn't do the holes very well. I guess you could say the holes are infinitely tiny. That's my stock reason. Now let me show you one where you have, yeah, I do see a velocity question from 2-3, but let me just kind of discuss the case because this is actually important. I want to discuss the case. This has come up in a few of the ed discussion questions. Differentiability at a point implies continuity at that point. So that is a safe assumption. That's a theorem, actually. Okay. So if a function is differentiable at a point, it's also continuous at that point. And really what's going on here is you have basically a smooth graph. All right. Continuity, on the other hand, if you go the converse of this statement, if you flip it, it does not, and I'm going to put a big old slash through it, imply differentiability. Okay. The classic example of that is like a corner. So you might have a graph like the absolute value function, which is just basically a V shape. It's continuous everywhere, but it's not differentiable at that corner because there's no way to put a single tangent line on it. Or equivalently, if you split it up as its constituent parts, you'll see that the slopes are -1 from the left, +1 from the right. Well, what is it? It's neither. All right. So this is actually a really important thing to know. Differentiability implies continuity, but the other way is not necessarily true. Now, if you have lack of differentiability, or I should say no continuity or discontinuity, so if you have straight up discontinuity, of course, you have no differentiability. Okay. The function's broke, can't take its derivative. Okay. Yeah. So yeah, you could put a point in. Yeah. So, a lot of you, I'm not sure, experiment with Desmos. I'm always learning. I'm still kind of in the learning curve myself with Desmos. What I do? I just look it up on YouTube. Yes, just learn that way. So if somebody's asking here, velocity word problem from section 2.3. Sure, we can do one of those. Let's go to that. Give me a second here to back out. Let me scroll down here. All right, looks like number 26 is a good one. We got a few of them. Yeah, 26 and 27. Let's look at 26. So I'm going to share the screen. So this is 2.3, number 26. The position of a particle moving on a horizontal line where s is in feet to the right of a fixed reference point, t is in seconds. It's given by s of t, which is t to the 4, take away 12t plus 15. We're told that t is starting at 0. Find the velocity in feet per second. All right, let me copy this down real quick. So we want the velocity, general formula, and we want it at t equals 3. We want all values of t where the particle is at rest. We want it where it's moving into the positive direction. And the total distance traveled during the first 8 seconds. All right, let's back out of that. All right, so I just wrote some notes to myself. It's not very fancy. The velocity function will just be the derivative of the position function. So 4t cubed, take away 12, and then that's it. Yeah, I know that part E is the tricky one. Let's do it at 3. You just pop in a 3, you get 4 times 3 cubed, take away 12. That's 27. That's 108. Take away 12 is 96. That would be feet per second. All right, so at rest. All right, so what we're going to do is we're going to take the derivative and set it to 0. Because that's where it would be temporarily stopped. So if you would solve, you get, if you move 12 over and divide by 4, you get 3. That means t is at the cube root of 3. And let me just pop a number out of that. I get about 1.4422. Okay, so at 1.4422 seconds, it's at rest. This is actually key for what happens next because check this out. If I put in, let's say, a 1, so one is to the left of 1.4422. If I put it into the derivative, I'm actually getting a negative velocity, which means it's going to the left, so to speak. Okay, so it's moving to the right, everywhere to the right of 1.4422. So for all t greater than 1.4422, it's moving positively or to the right. In between, so between 0 and 1.4422, it's moving to the left, or negatively, we would say. Okay, so this kind of brings us to this question right here. What's the distance after 8 seconds? Okay. So what we're going to do here is we're going to figure out, okay, at 0, we know that it was at 15. We know the position. So let me put the position values in. At 0, it's at 15 feet. That's its starting point. 15 feet, I guess, from the origin. At 1.4422, well, I got to put that into the original function. So let me do that. So just take the 4th power and then take away 12 times that number, 1.4422 plus 15, and I get 2.0198. So it's actually moved from the 15-foot position, it's moved left to that position. If in terms of just raw distance, that's 12.980 units. I'll just chop it there. So it's moved 12.98 feet to the left. Now it asks us up through 8 seconds. So at the 8-second mark, I got to figure out where it's located. So I put the 8 in the original function. So 8 to the 4th power, take away 12 times 8 plus 15, and I get 4,015. All right, now so when it moved to the left, and it actually temporarily stopped. When it was at 2.0198 feet, it stopped because it was at rest. And then it shot all the way to 4,015. So I've got to figure out what that difference is. That works out to be 4,012.98 feet to the right. So its raw distance is just the sum. And it works out to be 4,025.96 feet. That's the total distance. Righty. Loads of fun, eh? So why do you add not subtract? Because we are looking at the raw distance here. That was what the question wanted to know. It wanted to know the raw total distance. So, interestingly enough, when you talk about velocity, velocity is actually a vector and it can have negative values. We interpret that in daily life as basically moving from, or I should say, away or back toward a reference point. Now, if you look at your speedometer in your car, it's always a positive value. But technically speaking, let's say you were watching somebody drive away, they would have a positive velocity, but if they come back to your frame of reference, that's a negative velocity. So in this case, we had an object that started at 15, it moved left 12.98 feet, then it moved right 4,012.98 feet. And in terms of raw distance traveled, we just add them. All right, 2.1 question 1. Let me go to that. And again, I guess I'll be on the video if you need to watch it later. So I'm going to go to 2.1 number, I forget now, 2.1 number 1. Number 1. Okay, let me share the screen. 2.1, number one. We have a function h of x equals 2 take away 4x cubed. We want to know what the derivative value at 2 is, and then we want to find the equation of the tangent line at 2. Well, they give us the y value, which is nice of them. All right, let's do that. All right, derivative. By now, I think you've seen the short forms, which is nice, isn't it? So negative 12x squared. And then at 2, pop in a 2 there, you get 4. Negative 12 times 4 is that negative 48. All right, that's the derivative. And then we're going to, again, like that normal question from a few minutes ago, we use the old formula from algebra, the point slope equation of a line, and just pop our numbers in. You got to be careful. I'm going to write it out carefully. Be careful with your negative signs. Notice right here. So this is actually y plus 30. I'll go ahead and distribute the x. That's going to be plus 96. So then when I take away 30 on both sides, I get this negative y equals negative 48x plus, I guess that's 66. There you go. Again, if there's any questions on what I did, negative 12x, okay, how did I get that? Just using the power rule. So the derivative of a constant is 0. And then the derivative of a power, you bring the power down. So negative 4 times 3 is negative 12. And you reduce the power by 1. All right. Well, that was a lot of math right there. I'm still good to go. Anybody got any more questions for me? You can put it in the chat, or you can just go ahead and pop in with your microphone. If for some reason I've overlooked a question in the chat, feel free to remind me. I think I've gotten them.
Yeah, could you do question number 28 on section 2.3?
28 on 2.3. Take a look
Yes,
at that
please.
one. All right, let me show the screen. A spherical balloon is being inflated. Find the rate of increase with respect to its radius in inches r of the surface area in square inches. They give us the formula for surface area. You just copy this information down. 2.3, number 28. So the surface area is 4 pi r squared. Spherical balloon is being inflated. Let me read this question. I got to make sure I catch by its rate of increase. So they want it at r equals 1, r equals 3, and r equals 6. I'm going to come back to this one. Let me go ahead and get my overhead here. The derivative is just going to be 8 pi r. And when you pop in a 1, it's going to be just 8 pi times 1, which is 8 pi. This one is going to be 8 pi times 3, which is 24 pi. This one is going to be times 6. So 8 pi times 6, which is 48 pi. I'm gonna go back to the question real quick. I'm a little confused on something here. It's so with respect to its radius, and then it says in square inches per second. So there's a little units disagreement here. That's what's confusing me. We would assume again, I apologize for give me like 10 or 20 seconds here to kind of chew on this one. I think the problem is fine the way it is, but I'm debating whether they want it truly in terms of with respect to its radius. Yeah, that seems very odd. It's a very peculiar way to ask the question. No, actually, that's exactly what they want. All right. No, actually, what I did on the overhead here is perfect. All right. You know what? That's going to be one. I'm gonna bring that up. It's a good question. I think it's the only problem is it was talking about time. That was actually not implied in the original statement. So I got a little confused me a little bit. Okay, so we have a question here. Okay, Laura wants to see 1.6 number 2, and then we also have a question regarding derivative of sine and cosine. Yeah, the derivative of sine is always cosine. The derivative of cosine is always negative sine. That is true. And the other one you should remember is tangent. Its derivative is secant squared. And the rest of them, frankly, just derive them on the spot. If you ask me right now what the derivative of cotangent is, I probably couldn't tell you because I just don't remember. But I could tell you that cotangent is cosine over sine, and then I would work it out the long way. When you go higher in mathematics, you really don't see those other three trig forms. That is true. You don't see those trig forms because usually everything's written in sine and cosine anyway. And actually, that's not a bad idea to memorize them. Let's see, we have 1.6 number 2. Let me go to that. So again, give me a second to back out here. Share my screen. Okay, I got some limits. Oh, good. Let's talk some limits because you know those are going to be on the test. So we have a question here. Evaluate the following limits if needed. Enter inf for infinity and negative inf for negative infinity. These are exactly the same question. Is that supposed to be that way? I don't think so. Hold on. Okay. That is weird. Did that happen to you guys? Did you get the same question twice?
Yes.
Oh, you did? All right. That's a flaw. I apologize for that. I'm going to jot a note to myself. That's 0.6.
Oh, one of
Yeah.
them is positive, one of them is negative.
Oh, that's the yeah, it's a little negative down there. All right.
I do seem to recall a repeating question though. But I guess
That
it's-
happened. I taught the class sort of this summer. I know that happened at least once, and I thought we fixed them all. So, all right, let me copy it down. We have lim as x goes to infinity of 5 plus 8x over 9 take away 2x. And then the other one is as x goes to negative infinity. All right. Again, I would love to use Desmos because I think it's so cool. So I'm gonna go to my Desmos. Give me a second here. I'm gonna share the screen on that. There you are. So now here's what I suggest. Type it in as a function. Type it in as a function. And you get, you have to do a numerator. So it's going to be 5 plus 8x. And then on the denominator, you're going to get 9 take away 2x. I need to scroll out here. There you go. What we care about is the stuff way to the left and way to the right. Okay. And if you want, come down here and just type in like a big number. Okay. Type in even a bigger number. Oops. You ever see what I'm doing there? So I'm plugging in really big numbers for x, and you should be able to infer what the limit is. What does it look like the limit is? If I type in some ridiculous number, it looks like the limit is going to -4. And if I go the other way, let me pop some negatives in there. Same thing, it looks like it's going toward -4. Okay, so this is a really cool way to get to some limits here. And also, what I want you to be able to tell me is, okay, so in terms of finding limits, there's all sorts of rules out there, but honestly, I don't care how you find them as long as you find them. And in many cases, you use whatever works. Graphically is fine, as long as you're able to, that tells me that you at least have some understanding of what you're supposed to be doing. Now, one thing you can look at is when you have a quotient and you have the highest powers are the same, in this case, x and x are both power of 1, you look at their leading coefficients, and 8 over -2 is -4. So that's one way to do it. But let's say you forget that, well, then just put it on the Desmos and just work out some big numbers in this case. Okay. And then to interpret this is actually a line. I'll actually type it in, and it's a horizontal asymptote. The red line and the blue line actually never touch each other, but they get so infinitely close as that's what we call asymptotic behavior. Okay, so again, this is a good excuse to kind of talk about techniques for finding limits, because I have noticed, and I'm sure you have too, in the Edfinity, when they give you the solutions, a lot of times the solutions are written very high level, and I think sometimes I think it makes the problem a little more confusing than it needs to be. I'm okay with just kind of doing it by the seat of your pants as long as you do it correctly. Because when I teach this course, I really don't care how you find the limits. I care that you understand what they tell you. That's more important. Okay. Anyway, I think this is pretty cool the way this works out. So if you're going to do this, this is just like a quick and dirty way of, it's not really a table, but it's fairly easy to enter in the x values using the function notation. All right, I'm catching up on the, yeah, I'm catching up on the chat here. Section 2.2, question 6. Was that the one we just did? I think it was. No, I think it's 2.1. All right, let me go to 2.2, number 6. So let me back out. Oh yeah, and you know what? All right, I'm gonna share the screen. And this is more of a related to one of the earlier ones. So let's take a look at let's take a look at actually 3, 4, and 5 first. If f prime at 1 exists, then the limit as x approaches 1 of the function f of x is f of 1. This is just a fancy way of saying the function is differentiable at 1, therefore it is continuous at 1. And that is a true statement. Number 3 is a true statement. Differentiability at a point implies continuity at a point. Now, number 4 is the converse. If a function is continuous at a point, it is then differentiable at a point. That is false. And again, the stock example that you want to think of would be like a corner, the absolute value function. Number 5, if a function is differentiable at a, then is continuous at a, that is true. So really 3 and 5 are the same question, kind of. 5 is just written out in words, 3 is written out in symbols. Number 1, let's see, we got product f of x, g of x. If lim as f of x, g of x, as x goes to 1 exists, then the limit is the functional value. Not necessarily, it could have a hole there. Okay. And then number 2, as x goes, the lim as x goes to 1, the function is 0, and the lim as x goes to 1 of g of x is 0, then actually in this case it would be it would actually it does exist, so I guess it's false. It's like a negative of a negative, so it would be 0 over 4, which is 0. You can have zeros in the numerator as long as you have a non-zero in the denominator. So 0 over 4 is 0. If you get 4 over 0, that does not exist. If you get 0 over 0, that's indeterminate. That means it might exist. That means you need to do something else to figure out its answer. And usually, you can either factor and cancel, or if you don't remember that, just do a table. Depends on the function you're given. All right. Let me stop the share there. Also some messages. Question for honor lock. I have a bunch of tabs open in the web browser. Can I? Yeah, you should. In fact, yeah, this is going to be an interesting experience because this is the first time we're using Desmos on a test, and I'm kind of nervous myself. But yeah, it's gonna lock down everything else. So open up Chrome. I would actually go to Desmos first and get that page opened up, and then go to the honor lock page and then do its directions. I sent out an information in the ed discussions that helps you in case, for some reason, let's say you close your tab accidentally. Sometimes that happens. It'll tell you how to get back into it. Yeah. Yeah, I think it's going to work. I'm naturally anxious. I've got 250 students in this class, and even if only 10% of you have trouble, that's like, that's like crazy town for me. So I'm going to be spending basically tonight just kind of sitting by my computer monitoring things, making sure that everything is cool, because if there is an issue, I need to jump on it immediately. Reminder that the test is starting tonight at 7 p.m. Mountain Time. Right now, as I talk to you, it's 6:48 p.m. Mountain Time. You need to figure out what the time difference relative to where you are. Arizona does not do daylight savings. The rest of the country is on daylight savings right now, but we are not. We're always on standard time. So just figure out, just Google what time is it in Tempe, and then go off of that. And you have all day tomorrow up through midnight. So really you have what, 29 hours to do this test. Just a couple last things. The questions are taken from your homework. I think it's a reasonably fair test. I think when you're done with it, you're probably going to be feeling a bit of a headache, which is good, but I don't think you're going to feel it's an unfair test. If you've done your homework and you've been paying attention maybe to the videos and ed discussions, I think you're going to be okay. Historically, in history going back like a couple of years, the student success rate's been pretty decent. So, I understand it's taking a test is always anxiety inducing. There's no way around it. So, but I'm not trying to trick you. Just kind of go with the flow. If you do have a snafu with your computer or something, or you can't get in, email me. I'll try to help you. If you email me at 2 a.m., I may not get back to you immediately, but I'll be up pretty late tonight, just kind of tracking things. Yeah, last time I did a test with Unlock, it flagged all the other tabs, blah, blah, blah. Yeah, again, if you get flagged, as long as you're not brazenly breaking the rules, I look at each of the flags, and 90% of them are nothing. They're basically false positives. So, if you're trying to break the rules, yeah, you're going to get flagged out. We'll catch you because the video, it's hard to really cheat. But if it's an honest thing, like, some people are late, like the kid walks in while they're taking a test and starts talking, and they get flagged for that. Well, that's okay. Don't worry about that. If you got to stand up and stretch, that's okay. I'm pretty flexible about that. Just don't have like an obvious book and something open in front of you, that kind of thing. Alrighty. All right. We got 10 minutes. Does anybody have like any last immediate question we can do? If so, put it in the chat or just go ahead and verbalize. All right. Well, you know what, guys? I'm going to go ahead and power down. I'm gonna get this thing loaded. It'll be on my YouTube channel in probably about an hour. Someone mentioned you need to have the unit circle mentioned. Yeah, you should know at least the first quadrant. You're talking about the trig. You should know your first quadrant values, sine and cosine, and you can always develop tangent from that. You don't need to have second, third, fourth quadrants. And besides, you got Desmos handy. Basically, you just should know your standard angles for the first quadrant. All right, guys, thank you for the feedback. And good luck to you all. I'm going to go ahead and end this. 5, 4, 3, 2, 1. Bada boom.